start of Chapter 5. Chapter 5 begins with our discrete probability distributions, mean, variance, and expectation. So first of all, we'll revisit our definition of discrete. Discrete means it can physically be counted. Okay, the difference between discrete and continuous. Discrete, again, is a number that can be counted. We have 20 people in the room, or we have 28 desks in the room, something like that. Something we can physically count that are there. Continuous means they basically can be measured. If I say that I weigh 200 pounds, I might weigh 199.75 pounds or 200.666 pounds or something like that. So they can assume those decimal values in between. Discrete variables don't contain any decimals. They can physically be counted. So what we're going to be doing here to start with is finding the mean, the variance, the standard deviation, and also something called the expected value of a discrete distribution. So pictured here, initially we have a discrete probability distribution. A discrete distribution lists all of our possible outcomes. If I roll a single die, I can roll a 1, a 2, a 3, a 4, a 5, or a 6. And it also lists each of their corresponding probabilities. So probability of getting a 1 is 1/6, a 2 is 1/6, a 3 of 1/6, and so on all the way through there. So our discrete distribution lists all of our possible outcomes along with their corresponding probabilities. Once we have that distribution or that graph looking thing in place, the mean is found by multiplying each outcome by its corresponding probability and then adding those products together. So I take 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 and so on all the way through until I found the total of those, and that total would be our mean. So here's our symbol for a population mean. X of 1 times the probability sub 1, x of 2 times the probability sub 2, all the way until we have our last term, outcome times corresponding probability. Kind of a simplified version, that summation of each outcome multiplied by its corresponding probability. Find the variance and standard deviation is a very similar process. To find the variance, sigma squares our population variance. We square each outcome, multiply it by its corresponding probability, add each of those products together, and from that sum we subtract out the mean squared. So we just calculate the mean back here in our first process. We subtract out the mean squared. If somebody misses this, this is typically what they do. They forget to subtract out the mean squared. And from our work back in Chapter 3, we should also recall that the standard deviation is simply the square root of the variance. So if I found the variance, I take the square root of that to get my standard deviation. Sigma here is the symbol for our population standard deviation. One last term we'll have in this section is called the expected value. The expected value is essentially the mean, the theoretical average. It's just typically used when we talk about dollars and cents. So if we're talking about dollars, we're going to use expected value. Notice mean and expected value are the same thing here. It's the sum of each outcome multiplied by its corresponding probability. We just use this symbol instead of the mean symbol when we're talking typically about dollars and cents. That's not the only place, but for the most part, that's one of the common areas where expected value is used. So getting us started here, our first one to illustrate says find the mean, variance, and standard deviation number of spots that appear when a die is tossed. Well, we just had that distribution pictured on the previous page. We're going to recreate that. Our outcomes are 1, 2, 3, 4, 5, or 6. The probability of each of those is the same for each individual roll. 1/6 for a 1, 1/6 for a 5, 1/6 for a 6, and so on. So to find our mean, we multiply each outcome times its corresponding probability. So 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6 plus 5 times 1/6 plus 6 times 1/6. That winds up, notice all those have a common denominator of 6. 1 times 1 is 1, 2 times 1 is 2, 3 times 1 is 3, 4, 5, and 6. So our mean is 11, 15, 18, 21 over 6, or 3.5. So our expected value, or our mean, theoretical average is 3.5. Obviously, when we roll a die, we can't get 3.5 spots to come up with the number 3. But if we were to roll that die over and over and over and over again, our average should approach that 3.5. So our theoretical average is 3.5. To find our variance, we repeat that process, except we square each outcome. So 1 squared times 1/6, 2 squared times 1/6, 3 squared times 1/6, 4 squared times 1/6, 5 squared times 1/6, and 6 squared times 1/6, and we subtract out the mean squared. So here we have 1/6, we have 4/6, we have 9, we have 16/6, 25/6, and 36 over 6, and the 3.5 squared is 12.25. So here 1 plus 4 plus 9 plus 16 plus 25, 36. We have 61, 78, 86, 90, 91 over 6 minus 12.25, or our variance by using the calculator is about 2.92. So there's our variance. Running out of space here, so I'm going to try and squeeze my standard deviation over here. Standard deviation is the square root of the variance, so the square root of 2.92 means our standard deviation is about 1.71. So there's mean, variance, and standard deviation of a probability distribution, discrete probability distribution. We'll move on here. 3 coins are tossed, find the mean number of heads that occur, then find the variance and standard deviation. So our distribution, if we set up our discrete probability distribution, we flip 3 coins in the air, I can get 0 heads, 1 heads, 2 heads, or 3. 0, 1, 2, or 3. To find out those probabilities, we probably need a tree diagram. So heads and tails, heads and tails, heads and tails, and tails, heads and tails, heads and tails, and heads and tails. So out here I follow my branches out, heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, tail, heads, heads, tails. Let's try that again. Clean it up a little bit. It's kind of sloppy already anyway, so we don't get any sloppier than that. Tails, heads, tails, 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 heads, and tails, tails, tails. Oops, one too many terms. So our probability of 0 heads is down here at the bottom, 1 out of 8. Of exactly 1 heads is 1, 2, 3, so 3 out of 8. Of 2 heads, 1, 2, 3, 3 out of 8. And of exactly 3 heads is 1/8. Noting 1 plus 3 plus 3 plus 1 is 8/8. It adds up to be 1. So to find our mean, we'd simply take 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 and plus 3 times 1/8. That gives us 0 plus 3/8 plus 6/8 plus 3/8, or 12/8, which means our mean is 1.5. Okay, same thing applies. We can't flip a coin and get 1.5 heads, but if we were to do that over a period of time, our theoretical average would approach 1.5 heads showing up. To find our variance, we square each outcome, so 0 squared times 1/8, 1 squared times 3/8, 2 squared times 3/8, and 3 squared times 1/8, and we subtract out the mean square, so subtract out 1.5. Here we have 0, 1 squared is 1 times 3/8 is still 3/8, 2 squared is 4, 4 times 3 is 12/8, and 3 squared is 9, 9 times 1 is 9/8, and 1.5 squared is 2.25. 15, 24 eighths, so we have 3 minus 2.25. Our variance is 0.75. And again, one last time, our standard deviation is the square root of 0.75, or in this case, 0.87. So there's our variance and our standard deviation on top of our mean. Moving on, we have a couple that involve some dollars and cents. A store finds the following results for profits and losses each day. Profit of 1,000 is 0.4, loss of 2,000 is 0.3, loss of 1,000 is 0.2, and then profit of 5,000 is 0.1. We're going to find the expected value. So as I mentioned earlier, the expected value is the same thing as the mean. Now we already have this set up in a distribution format. It's just vertical instead of horizontal. So we're going to go ahead and find our mean by taking 1,000 times 0.4, negative 2,000 times 0.3, negative 1,000 times 0.2, and 5,000 times 0.1. So down here I have 400, I have negative 600, plus negative 200, and plus 500, or our expected value is $100. So we can expect to make a profit of $100 each day. Okay, so that's a good thing. If our business is making a profit, we're going to stay in business. If this were a negative number, we're losing money on average every day, we're not going to stay in business very long. Now for the variance or standard deviation, I'm just going to make 1 point here. I'll let you go ahead and calculate that. But if I were to start to set this up, I'd have 1,000 squared times 0.4 plus negative 2,000 squared times 0.3. So I just want to make a calculator point here with that negative 2,000. If you type that in as negative 2,000 squared, that gives you a negative 4 million. Okay? Well, if I'm squaring negative 2,000, negative number, it shouldn't be negative. So be careful with your order of operations here. If you're going to square a negative number, it should be in parentheses. So you square the negative and the number itself, so it's a positive 4 million. If you get a negative 4 million versus a positive 4 million, there's a big swing right there. That's going to affect your standard deviation or your variance quite a bit. So just making that point. We've already done the standard deviation and variance twice, so hopefully we understand that process. I'll go ahead and write them out and you can make the calculation yourself. Negative 1,000 squared times 0.2 plus 5,000 squared times 0.1, and from that we're going to subtract our mean, which is 100 squared. Notice that's all underneath the same radical. That's our setup. We could go ahead and solve it from there. Find the expected value and the standard deviation. We're going to skip the standard deviation side of things just to make life simple. Expected value for winning $1,000 if 2,000 tickets are sold and you buy one ticket for $1. Now there's two different ways to set this up. I'm going to set it up with what I'm going to term the net proceeds method. So there's two different things that can happen here. We can lose $1 if we don't win, or we could win this $1,000 prize, but notice I don't get my dollar back, so in the net proceeds I actually win $999. If I paid $1, they give me $1,000 back, so my net profit is $999. Okay, so my chances of winning, I only have one ticket out of 2,000 tickets, which means my chances of losing are $19.99 out of 2,000. So my expected value, again, is the same thing as the mean, and that mean is $9.99 times 1 over 2,000 plus negative 1 times $19.99 over 2,000, or $9.99 minus $19.99 over 2,000, which is negative 1,000 over 2,000, or my expected value is to lose 50 cents. Okay? Never want to lose money, so losing 50 cents for each ticket I buy is probably not a very good idea. The more tickets I buy, the more money I'm going to be expecting to lose. Okay, so we'll go one more time here. 1,000 tickets are sold at $1 each for 4 prizes of $100, $50, $25, and $10. What is the expected value if a person purchases 2 tickets? Set up my distribution. X and the probability of X. Prizes. We're buying 2 tickets, so each ticket costs $1. If we win $100, we spent $2, so we're actually winning $98. Or we're winning $48. Or we're winning $23. Or we're winning $8. Or if we bought 2 tickets, we could lose $2. Since we have 2 tickets, we have 2 chances to win. So 2 out of 1,000 tickets, 2 out of 1,000 tickets, 2 out of 1,000 tickets, and 2 out of 1,000 tickets. So notice then our probability of losing $2, 2, 4, 6, 8 is 992 out of 1,000. Our distribution probability should add up to be 1. So 2, 4, 6, 8, and 992 is 1,000 out of 1,000. Our probabilities add up to be 1. And now our expected value is our mean. That is 98 times 2 over 1,000 plus 48 times 2 over 1,000 plus 23 times 2 over 1,000 plus 8 times 2 over 1,000 and minus 2 times 992 over 1,000. I'm going to jump straight to my calculation here since I ran out of space. But if I take 98 times 2, I get 196, 96, 46, 16, and subtracting 1984. That gets me an expected value of negative $1.63. So if I'm spending $2 and losing $1.63 of that on average, not a very good deal for me, especially from an investment perspective. So there is our look at expected value, mean, standard deviation, and variance.